everyone. Let me introduce our resource person today for shallow foundation and industry practices and special topics. Engineer Vimalaraj. Engineer Vimalaraj is a geotechnical engineer in the USA with more than 16 years of experience in the design and construction of numerous large roadways, buildings, power plants, and other infrastructure projects. Engineer Vimalraj is currently the owner, president, and principal geotechnical engineer of Corestone Engineering, which is a geotechnical design and consulting firm based in Reno, Nevada, USA. Engineer Vimalraj is a licensed professional engineer and geotechnical engineer. Engineer Vimalraj graduated from the University of Peradeniya in 2002 with a B.Sc engineering honors degree, specialized in civil engineering, and worked at the university through August 2004 as temporary instructor and lecturer. He received M.Sc in civil engineering with geotechnical courses and research in May 2006 at the University of Nevada, Reno, USA. He then joined a local geotechnical firm, Black Eagle Consultancy. As a geotechnical engineer, technical staff working in the soil assault concrete testing lab, and progressed to the vice president of the firm through multiple promotions, including project engineer, project manager, and engineering division manager. In January 2021, he left his job and at the previous firm and now working at his own geotechnical engineering firm. In his career, Engineer Vimalaraj has co-authored over 1,000 geotechnical investigation and design reports, and was a lead geotechnical engineer for numerous major projects, including Tesla Gigafactory, Nevada, more than 13 million square feet of floor space when completed, Southeast Connector, a major roadway in Reno area with US $300 million design and construction cost, Amazon distribution facility in Reno, and several geothermal and solar power plant projects. And over to you, Engineer Vimalraj, for the presentation.
Thanks, President. Thanks for the introduction. Yeah, it's a privilege to do the presentation for you guys, the engineers in Sri Lanka and all over the world, Sri Lankan engineers. So without further delay, so I would like to get into the presentation. So it means as a geotechnical engineer, so I have been working for 16 plus years, you know. So the main thing is you had to do a geotechnical investigation report. The main focus of the report is usually it's for a building or bridge or, you know, whatever the infrastructure. So everything starts from the foundation. So the main purpose is you had to investigate the soil or rock, bedrock, all the subsurface materials to develop recommendation for foundations. So usually we start with the shallow foundation. So that's a straightforward support for the building rather than, you know, going into the deep foundation. So that's the first step, you know. So if you take in Sri Lanka and everything, even here, so most of the structures, like 90% of the structures are supported by shallow foundations because that's probably the most cost-effective foundation. Because yeah, to construct deep foundation or any other special foundation, so you need a specialty contractor. So that usually end up costing more money. So every project is, you know, so they build this building or house and everybody want to save money. So we start with the shallow foundation. So I want to, I want to go over some basic, what we learned in the university. So probably a foundation engineering or geotech course, just the basic information. Then I want to go over how we approach, because I do like, every month through my firm, I do like a geotechnical investigation reports, like 10, something like that, is 10 to 15 geotech reports and design reports. So everything is, all the reports are for buildings or even like, I don't do much residential project, mostly commercial and industrial projects, and some government projects. So everything, most of them are focused on, buildings, like large warehouse buildings, 1,600,000 square feet. So I apologize for the unit, because here we are used to the US customer unit. So yeah, like mostly I'll talk in feet, inches, or pounds, but it's probably a little bit complicated, with the kilogram and meters and everything. But here US want to be, they don't want to change because British introduced, but they want to just keep it. It's hard to change here, so that's the unit we use here. They tried to change in some government states, but it didn't work out. So still in the feet and everything. So one of the few countries use the feet, pounds and everything. Anyway, so we do a lot of geotech reports, and main focus is the shallow foundation. So we start with the foundation. Shallow foundation is the main focus. Then if the shallow foundation doesn't work because of the soil conditions or anything, like bad soil condition or structural load is high, for example, large bridges and everything. So if your load is high, then you may have to go into deep foundation, but it's very rare unless you have because here in this area, like usually most of the structures are 5-6 stories, except the downtown area. There are like a 30-40 story structures. Even that one, they will try to put it on mat foundation with the parking garage and everything, but it's hard to, it's very rare to put deep foundations, except some bridges, mostly shallow foundations. So that's the topic I'm going to cover it. So I work on my own firm. So he already introduced everything, and so let's go to the next slide. Okay. So the main thing is shallow foundation. You want to know about the bearing capacity. So bearing capacity, that's the main thing, because if you have a load, you want to design the foundation to support the load. So if you have a particular load, you are going to size it, whether it is 2 feet in 1 meter in width, or 3 feet in width, or like a 3 by 3. So then you had to find out what is your bearing capacity of the soils. So bearing capacity means, so there are two things. So you had to consider two. The main thing is true soil capacity. So how much the soil can take before it can fail. And then there's a settlement. So this usually, so you don't put the foundation on an not compacted soils. It means, you had to prepare the soils and place the foundation on the prepared soils. So the soil failure, true soil shear failure, is very rare. So in most cases, the settlement controls. So you want to limit the settlement to, say, 1 inch, 25 millimeter, because for a foundation, that's kind of a typical permissible, tolerable settlement value before your structure start to show like a structural distress, cracks and stuff. And so we like to limit the settlement, the long-term settlement, to 1 inch or less. So that's the main. So first one is the true soil capacity, then consideration to the settlement. So you calculate based on the true soil capacity, then you calculate based on settlement. So yeah, you can limit only 1 inch settlement. That's the maximum possible, because before there's distress in the structure, then you limit it to 1 inch. Then you calculate your bearing capacity. Then whatever the less value, you define, So in a report, geotech report, we will typically, like for a project, we'll have a particular value. Okay, so allowable bearing pressure for this square and rectangular foundation, a particular value, 2000 PSF or 3000 PSF. I don't know how it converts into Newton or Pascal. Yeah, Newton. But yeah, so a particular value we will give. Okay, so then structural engineer will use that value. And so other factors like sliding factors and everything. So they will consider those values, and for the load, they will design the size of the foundation. And so that the geotech report will have those recommendations how to design the shallow foundation. So the true soil capacity. So you might be familiar, everybody, like a 3 terms, equation, Q ultimate. You calculate your ultimate bearing pressure. Then you use a factor of safety, generally 3, factor of safety of 3 for the static loads. If it's a earthquake loads, you can reduce the factor of safety. So then you calculate your ultimate and divide by a factor of safety. Then you will get your allowable bearing pressure. That's considering the shear failure in the soil. Then, so depending on your soil layers, if it is compressible soil, so with the load application, it's going to settle. So then you calculate your settlement. Then you can, if you end up like for a particular load, 2000 PSF, if you end up getting more than 2 inches of settlement, you cannot recommend 2000 PSF. Then you have to reduce it to 1500 PSF. Then calculate, if it is 1 inch or less, then you recommend that value. So this value is the one going to control most of the time, the settlement control value. And so when it comes to the bearing capacity terminology, ASD, I'm not sure if we have started to use LRFT. Ramanan, do you know? Have you started LRFD? No, or ASD mostly now?
We are going with ASD, it seems.
Oh, ASD. Okay, so here it's everybody is changing to load resistant factor design. So for the roadway, bridges, and everything is now like the government structures mostly LRFD, but otherwise private projects still ASD, allowable stress design. That's what we learned even the university. But now it's LRFD. Everybody like ASTO and everything is changing the LRFD codes. So everybody's familiar with that. So you have 2 values, just ultimate and allowable. But if you go to the LRFD, that's nominal, factor, then strength, service. There are so many limit states you need to consider. And so mostly like a nominal and factored. Sorry. So nominal and factored. So I just want to introduce the terminology. Okay, so different methods have ASD and LRFD. The methodology is like a terminology is different. So the next one. So I want to talk about the true soil capacity. So that's totally a 3-term equation. So you have first component and second component and third component. So you have a lot of factors here, except this the basic component. So first one is soil cohesion related. If it is if the soil has a cohesion, say for an example, if it's a clay soils or something like that, if it has some cohesion, you can consider those values. And the second component is effective stress at the footing depth. So whatever the depth you are placing the footing, so then that second term is dependent on that one. The third term is half the footing width below the footing, bottom of the footing. So if you place the footing deep enough, then you can provide a higher bearing capacity. So because this term is going to depend on that value. That's why even if you have only support a big like a 30-story structure, if you want to put like a 2-3 parking garage below, then yeah, you are going to put your foundation way deeper than the finished grade. Then yeah, you're going to have a pretty large soil bearing capacity. But yeah, then you need to consider the settlement. So this is the basic equation, and there are several methods. So Tesahi, Mayhoe, Hansen, yeah, all those, they give like a different factors, and even the NC, NQ, N gamma, those values will vary. They're based on your friction angle, NC, NQ, N gamma, but they have different equation. Everything like kind of learned, and then these factors, they are based on your shape of the footing. What is your footing inclination, load, if the load is acting on a direction. For example, in the retaining wall is the case, so you're going to have a stem and supporting a soil, then you are going to have more lateral load. Then you need to consider that load inclination, how it acts on the footing to calculate your bearing capacity. And a nearby slope, if you have a bridge apartments, because you're going to have a slope right near the foundation, bridge apartment foundation, then you need to consider that slope, because whenever you place the footing next to the slope, you're going to have a global issue. Then they accommodate that one, those factors, nearby slope. So the next one is, okay, so I'm here just writing down the entire equation with different factors. So you have tables and formulas for these factors based on your, shape factors, depth factors, load. So if you have a shallow groundwater, it's going to affect this Q value. So then you're going to have a less bearing capacity, because your Q is the effective stress, because shallow groundwater means you're going to have less effective stress. This component is also going to affect it. So that's why you'll have a true soil shear-based soil capacity will be less if you have a shallow groundwater. That may be the only case it may control on a shear failure based. So yeah, so I didn't want to write all the equation and everything, because then so it's like different cases. The typical case is, okay, yeah, you use your C and NC. So there's most of the cases, if you have a square foundation, yeah, it's going to be one, all this. There are simplified version, but yeah, in reality, you had to consider everything. But the typical cases, you're going to put it on a flat ground and at some depth and your foundation, so it's easy to calculate your shear based. I don't, whenever I do the geotech reports, based on your soil condition, and once you see the logs and everything, you could do some calculation, but in most of the cases, with your experience, you should be able to, you can predict, okay, so this is what, it's going to work for the particular soil condition. Then you can do some back calculation and check it. So these are the bearing capacity factors, NC, NQ, and gamma. So this is Tesahi. So the Tesahi is the one first, introduced the bearing capacity. So he's the father of geotech. And then, so everybody modified, Hansen, Mayer, basically introduced different factors and everything, and they calculated this value. So everything like a little different. NC and Q is same, but N gamma is different for these all these authors. So bearing capacity. So how the failure, because this is shear failure. So there are like three cases how the footing can fail, because it's a shear failure in the soils. So it could be a general shear failure, means this is the most common one. you're going to have a failure, going fairly deep. That's why your half B terms, if the footing is B in width, so you go half B. So that's why, because this general failure is the most common term, common type of failure. Then you have local shear failure. Punching shear failure means just footing, just sink into it, because unless if the engineer is bad or contractor is bad, then you're going to have a loose soil, soft soils at the base of the foundation. Then it's going to have this kind of punching failure, but it's very rare because you have with the construction control and everything, and because you're going to compact the soils and you're going to prepare the soil properly, then this kind of punching failure is very rare. And this is in between local shear failure, but the most common case is a general shear failure. So this is how if you consider punching shear failure, there are factors you need to apply to calculate your bearing capacity, the actual ultimate bearing capacity, because you need to, if you think there's a punching failure, possibility of punching shear failure, then you have to reduce your bearing capacity, obviously. Okay, so this is so I have like a spreadsheet developed for various methods. So always I do is rather than considering just one method, then you can consider all these methods. There'll be a huge variation. So for example, this is just a square foundation, 2 by 2, like a 0.6 meter by 0.6 meters, as placed at 2 feet depth, and if your cohesion is 0, in most cases, you don't want to put clay-rich soils here. Like you can assume this soil cohesion is 0. So angle of internal friction. So if you have the lab testing or anything, so you can put that value. Then unit weight of the soil and the groundwater table. If the groundwater table is shallower, then the bearing capacity will go down. So I usually have a spreadsheet to calculate all these methods and get your average. Then I recommend what is the value. Then you have to consider the settlement also. Then we'll go with the recommendation. Then if you have this is for a particular footing size. If you have, let me go into. Let me show the spreadsheet. So what I do is, so it's based on your true shear failure. So you can use if you have a building of various foundation sizes, then I calculate for different width. This is a continuous, because if you have a building on the edge, you might have a continuous wall foundation, and like on the corners, some places, you will have your column foundations. Then you calculate for different foundation width and sizes, and then you can recommend net allowable bearing pressure. But if you see there's an important note there, you need to consider the settlement, because that might be the one controlling most cases. So then you just check it here. And then when you calculate your settlement, then you can recommend a particular value. Then this will be used by the structural engineer to design the foundation. And let's go to the... Okay. So when you go to the settlement, so when you apply the load, foundation load, you're going to have settlement. Depending on the soil conditions, there could be immediate settlement. If you have clays with the shallow water table, you could have consolidation settlement. It could be primary, even secondary, even creep for a long time. It could happen. And then there's one called self-consolidation or internal compression. It's usually, we don't learn much in the the university or anything. But here it's a very important thing, because whenever you have a large site with a lot of cuts and fills, because here not all the sites are flat. Some places you have flat sites, but if you go to a little bit of on the hillside, so you're going to have, because if you are going to have place a 1,000 feet by 300 feet building, 300,000 square feet building, that's a large building. If you want to place it in a flat ground, you need to place, if the ground is sloping, there will be a lot of cuts and fills. So you'll cut one side like a 40 feet, like a 10, 15 meters, and one side you'll fill it 15 meters. 15 meters filling means, so you're going to place those fill as compacted fill. But still what's going to happen is, when you place the fill on the bottom fill, so you placed it in let's say 0.3 meters, 1 foot, thickness. Then you put another thickness and compact it. First compacted, then second compacted. Whenever the bottom layer is going to settle because of the weight of the overlying fill, whenever you put it place, it's going to, because you're going to apply a lot of load on the bottom layers, each layer. So that fill could settle. So yeah, that's the settlement you need to consider, because if you have a huge fill site, then we consider that one also. Then we ask them to put if it is more than 5 meters fill, so like 15 feet fill, then usually I recommend, okay, so yeah, they need to wait until the fill settlement is complete. Say 1 month, 2 months, then we put some settlement monitoring point and just measure, because this is not from any native soils, because within the fills there could be some settlement. That's usually half to 1% of the fill height. We have recorded several projects and everything, so we have a kind of a half to 1% is a typical value we see. And then we can either you account in the design. Okay, so if you can tolerate up to 10 feet of fill settlement, then okay. So then you don't have to do anything. Then if it is 20 feet of fill, then if there's some waiting period needed, you need to recommend that one in your geotech report, because otherwise what they will do is, once the pad is prepared, cut and fill, then they'll start to place the foundation. Then those foundations are going to pick up those fill settlement. Then once you build your walls and everything, so there could be some cracking. So here it's always careful. Whatever you want to address, you need to address it. Otherwise, you'll be in the middle of the lawsuit. So other settlement issues, the seismic settlements, of course, earthquake regions, like here. We could have significant earthquakes, like a magnitude 7, and so then you had to look into, if you have loose soil, or like a soft soils, can there be any seismic settlement? Liquefaction, you may have learned it. Liquefaction is, whenever you have shallow groundwater, loose to medium in sand, it could liquefy, means it can turn into like a water-like. Then it will have the potential to cause some settlement, because not the entire layer, because in this area, we don't see a 10-foot layer of liquefiable soils, but there are some areas, you might have like a 2-3 feet, 1 meter, like a interbedded layers, liquefiable layers. Then you need to calculate those settlement, and you need to provide in your report. And if it is too excessive, how to address, whether you want to go do deep foundation, or can you do some ground improvement? Those recommendations, everything should come in the geotech report. And if you place the building right next to a slope, could there be any a slope instability that could add to some settlement to the foundation? So those are the things you need to look at it on the overall side. But if it is a large project with slopes and everything, so everything is to be carefully looked at it before you prepare the geotech report. So bearing capacity settlement criteria. So typically, like on a small project, I'll have just a particular value. Okay, so yeah, use 2000 PSF. If you take like a IBC and everything, so like they have a minimum recommended values, International Building Code. Usually for any soil, you can use 1500 PSF. Even like a bad soils, even the structural engineer without geotech report, yeah, he could assume of 1500 PSF. And yeah, they have some kind of values. You can use this one without a geotech report, but in our report, yeah, we will recommend whatever we calculate. So we don't have to depend on the building code or anything. So that's why they do all the time, like the projects, they need a geotech report so they can economically size the foundation and address any soil issues. So yeah, there are like sites with the soil problem. So they want to find out those things. That's why here in the US, yeah, like in this area in the US, geotech report is important. So this is for a bridge project, a bridge project. So this is LRFT based, so various footing with, pier footings and abutment footing. So you have to recommend the minimum embedment depth, and this factor bearing resistance means it's based on your true soil failure, allowable bearing pressure like in ASCE. This is service means it's depend on your permissible settlement. So you can provide us a table with the footing with various footing width, or you can provide as a graph. This is your shear failure. What's going to happen is because the term has a B. So whenever your footing width increases, your true shear failure, that value is going to be your allowable bearing capacity going to increase. But for the settlement wise, whenever the footing width is going to increase, your load influence on whatever your load, you apply a load, that's going to affect even deeper soil. So that's why whenever your footing width increases, you're going to get lesser and lesser allowable bearing pressure. There's a certain point, yeah. So it might make sense to design the foundation, but yeah, you need to pick, like if your footing width is 1 meter, the structural engineer will go and pick this value. Okay, this is the lowest because, so you need to consider everything, all this. If it is a 1 inch settlement, that's what you want to consider. So he wants to consider this curve and this curve. So if it is let's say 1 meter, so he goes there. So this is the value he has to use. Okay, so it doesn't work for the load, then he will pick another load. Okay, somewhere here. So yeah, sometimes like on a large projects, like bridges and very large buildings and with significant structural loads, yeah, you'll develop a curve like this for a site. Then it'll be easier for a structural engineer to pick these values depending on the footing sizes. So those are the typical bearing capacity, like theories. But there are some soil conditions, other unsuitable soil conditions. So here there's expansive soils. If it clays, if the clays are very dry in the native state, it can absorb water and it can expand. So that's bad, so because you calculate your settlement, but the expansion is a problem too. If the footing lifted up, then you're going to have problem to your house and the building. So that's very important. So here we have to investigate the expansive soils. If there's a clays, how to address. You can, the common procedure is, okay, yeah, you remove like 0.6 meter to 1 meter and replace with the good soils. Then you are not placing your foundation on the clays, expansive clays, because whenever the clays are buried deeper, so it's very less chance for the water to get into the clays and for it to expand. At least that's theory. And so you could do some other alternate design. They're like here the houses, they will design like post-tension slab foundation that can tolerate this some expansive movement in the clays. For a large buildings, it's hard to do the post-tension slab because of the spans and everything. But here, like they can do drill piers with the bell bottom, because you put a drill shaft, and then if you have a bell bottom, means like it goes down a little bit this way, bell bottom, then it's hard to pull it. So there are some places here in this area, because whenever I do the geotech in those report for those some projects in some areas, I had to be really careful, because I know there are very, very bad expensive clays, and then I had to investigate everything and do the right testing and provide the correct recommendation. So typically expansive soils, you can do the lab testing, you do the site investigation. I'll talk about the field investigation a little bit later, but you can do the field investigation and then do the lab testing. Typically you do the Atterberg limits. It gives you your plastic limit and the liquid limit, and you can calculate your plasticity index. If this index is plasticity index, it tells you how sticky the soils, clays, how sticky. If it is very, very sticky, that's going to, because it's going to absorb more moisture and it's going to expand more. So that's a that's a bad thing. And then you can do the expansion index testing in special test. You can do that one. It will tell you how much expansive it is. And so you do this testing. If it is really bad, then I will go ahead and do this test also, just to confirm. And another category is collapsible soils. In Sri Lanka there may be, but in some regions, here also there are some regions there are collapsible soils, because they will be kind of very strong when it is dry, but whenever it gets some moisture, it can just collapse and causing a lot of settlement, because there are certain criteria you can identify the collapsible soils. For example, here. So the collapsible soils, this is a very useful diagram. So we always, in this region, collapsible soils are less. But if I go and do some projects in some other state, I had to always check this one, because if I don't know the soil conditions, I had to make sure there's no collapsible soils, because this is bad, because it can just suddenly collapse, and then it can cause catastrophic damages to the buildings and stuff. So it depends on your liquid limit and your natural dry density. So this is the criteria curve. If that point, the soils falls in this one, if you have 80 PSCF, whenever you have density is less, it means density is less means that the soils are, so they are not packed together. They're kind of, what do you call, like a bounded together with the some kind of cementation, but you have voids. That's why, because usually the soil is, if it is compacted, it's like 125. If you have a very less dry density and liquid limit is like that, then you won't have a collapsible soil, so you can identify easily. Then you had to address those kind of soils. You need to put a deep foundation, or remove and replace as a compacted fill, because once you remove the soils and you recompact it, then you are removing the collapsible potential, essentially. Okay, so whenever you want to recommend bearing capacity, everything in the geotech report, you need soil information. You cannot just assume, okay, so that's the site here in this address. So let's use a 30-degree angle and let's give all the bearing capacity and everything. But so then you will end up in the middle of the lawsuit. Here it's usually like that. So you have to be careful. Then you need the soil information. Then how much soil information you need? If it is a small house, you will dig down like 5 to 10 feet. That's enough, because usually we try to go 2 times the width of the footing. So usually if it's 3 feet, yeah, 6 feet should be enough. If you know the soil information to 6 feet, you can provide the recommendations, all the bearing capacity and everything. But if it is a bridge foundation, yeah, so you're going to have a larger loads and bigger footings, then yeah, you may have to drill borings to 100 feet. That's, if it is a bridge and everything, that you have this government ASTO guidelines you need to follow. Typically, you need 100-foot borings and everything. And also, yeah, if you have some, even a small building, if it is in a problem area, let's say like a liquefiable soils because of the earthquake, then yeah, you need to do the right exploration, borings or test pits, and you have to do the right field testing to get your soil information. So site exploration, it can be test pits, borings, CPT cone pantorometer testing, and other field testing. Then you will collect the samples and you can do the lab testing. Typically, these are called gradation C-value analysis, and at the back limits, the soil, very basic testing that gives you the information. Then you can, there are like so many like published charts. You can figure out phi value, and if it is a large enough projects, and then you can go ahead and do direct shear, triaxial, and just to confirm those phi values and everything. But if you know the soil condition, yeah, like if the site is all sand and it's all, there's not loose layers or anything, so then yeah, so just couple of index testing just to confirm your field logs and everything, then you can develop all the report and recommendation, because there's no, like all the project has a limited budget, so you cannot do like all. If it's a large enough project, yeah, we can include a direct shear and everything. But yeah, like if the project is small enough, then you have the budget also small enough. You don't have an unlimited budget on the geotech. Then you have a particular budget. Yeah, you give the proposal, and within that proposal, because it's competitive. Because yeah, like if I give for a small house, and if I want to do the geotech report, and if I say $10,000, then somebody else is going to get the projects, so that's why you need to know the soil condition, then you can include the right amount of testing, and you can limit the budget and get the project. So this is test pits, and it's one of my project. So yeah, we use the backhoe, excavator, depending on, if it's a hard soils, and if I want to dig down like a 20 feet, 25 feet, I will use a large excavator. This is a trench. So I don't want to get into some earthquake faults and everything, because yeah, this project had some earthquake faults. You cannot, here there are regulations, you cannot put the building on the fault. So you need to identify the faults, that's not my expertise. I had another geologist, he did the earthquake fault punches, so they can identify the fault if there are some faults, earthquake faults. Then because yeah, once they investigate, I will also log the soils and what kind of soils and everything. So I'll collect sample, prepare the logs. Okay, so this is borings. We don't do cone pantorometer testing. It's pretty in this area. The soils has a lot of gravels. Typically, if you have clays and everything, because CPT is you push and push a cone. Then depending on your risk, and yeah, you can figure it out whether it's what kind of soils and what kind of properties it has. But here it's hard to push those, because yeah, we have a lot of gravels and cobbles, and it's hard to do everywhere. So we typically do the borings. It could be just a standard hollow stem auger borings with the SPD testing, standard penetration testing. SPD testing is it's a measure. You drive the sampler, 6 inches, 6 inches, 6 inches, 0.3 meters interval. Then last 0.6 meters, whatever the block counts, that's called SPT block count, field block count. Then you can convert to, so you can adjust it, and then you can. There are like all the charts and everything. Like in the geotech literature, you have these charts. Then you can use those block counts, average block counts. Then you can calculate the friction angle, and you can do the settlement calculations based on those block counts. And it's very helpful, SPT block count. So we always do the borings when you get your samples. At the same time, you do this standard penetration testing, because those samples are the one you drive it. Then you are going to have those block counts. At the same time, you will pull those samples, and you can test them, and you can log them. And other testing means, let's see. Okay, so this is like a standard boring logs, So you do the SPT blows in the last 12 inches. That's your SPT field block count. It will tell you the soil. Okay, so this was one of my projects, and so you log them. So this sample will come out. It's silty sand with gravel. Then we can log with the fines and sand, gravel, how much percentage and everything. Then I will do a lab testing right here, the lab test results. So it will exactly tell me what is your electrical limit and plastic limit. Then I will, I can confirm my field logs, and then you'll prepare this boring logs or test pit logs. Then you have all the information throughout the site, and then you use those information to develop recommendations. So it's not only, because the main recommendation is your foundation for a building, but there are like so many other recommendations you had to do. So another, some other testing is geophysical testing. You can measure the shear velocity with the geophysical. You have this geophone sensors, and there's a data unit. So it will collect your data, and you can model the shear velocity. And this is useful whenever you do the seismic classification and stuff. And then that's useful. And then you can do the geophysical testing to find out your P wave velocity, because if there's a bedrock site, they want to know whether they can excavate the bedrock. If it is soft enough, you can use the dozer and rippers and everything. They can excavate it. Otherwise, if it is strong, if it is very hard, you need blasting. So those kind of information, if I need those information, I will do bedrock coring, and then you can do this kind of geophysical testing. Then you can correlate to charts and everything. Then you can figure out whether you need blasting or you need you can excavate. Okay, so I just want to cover the geotechnical investigation report. I'm not sure how frequent in Sri Lanka they do geotech report for projects, but here it's for a single family houses, like a small houses, you don't need it, except some regions, some cities and some county might tell, okay, you need a geotech report to build a house. But if it is a commercial project, even a small coffee shop, typically you need a geotech report. In this city, in this county, all these different cities and states have regulations. You need to have a geotech report for this kind of projects. But the thing is, even a house, if you want to build a house, then what the city will tell you is, okay, you don't need a geotech report, but when you build the foundation, somebody needs to certify the soils. Then so they will call, we need somebody to certify the soils. Then we'll have to go and take a look at it, and whatever the design they use, the bearing capacity, is the soils are good enough? Do you have expansive soils? And those are things we will evaluate that time when they do the construction for a small projects. But like most of the, if you want to build it right, and well, like house owners, they will want to, they like to get a geotech report done, because if you have expansive soils and problem soils, it's a problem, because you're going to have cracks and you're going to have settlement. And the homeowner, if they are spending a lot of money on the house, they don't want that one, and they want somebody to blame. There'll be a geotechnical engineer, so then they will hire a geotechnical engineer to do the geotech report, so that they have a backup. Okay, so they already looked at the soil condition and number of things. That's why, because they rely on us, so we have to do the good job too when they spend the money. Okay, so if the cellar foundation doesn't work, what we do? So we can do soil improvements or other foundation alternates. The soil improvements, okay. So if you have very soft soils, you're going to put a building. We have very soft soil with the compressible nature. Then because when you put the building foundation load, whenever it's applied, you're going to have settlement. That's not acceptable. What you can do, maybe if it is a small enough house, so you don't have to replace the tons of load, then you can replace to 1 meter or something like that, then replace with a good soil, then you should be fine. But if it is a very large building with large load, removal and replacement, that wouldn't work. The clay soils also, you can remove and replace. But if it is a compressible soils and through very deep, if it is going 10 meters, 20 meters, and if you have a large building and with a large loads or bridge, and then removal and replacement wouldn't work. But the dynamic compaction is, it's usually, if you have a loose soils, you drop the weight, and you try to compact, and because they will have big cranes, and I think there are some projects in Sri Lanka I have maybe they may have used it. And that's, you densify the soils. If you have liquefaction issue, like in the shallow depth, like a 10 meters or like 8 meters or something like that, you can do the dynamic compaction. And deep soil mixing is you mix it with the cement and the soils, then you improve the soils. That also increase the strength. Then you can you are reducing the settlement potential, and you are improving the bearing capacity. Or even if you want to build a road, it's a subgrade, and you are dealing with the loads. So then you improve your soils, and vibro replacement. You vibrate, and you try to you vibrate the probes and put some aggregates, so then you vibrate at the same time. You just introduce the aggregates, and it densified. And stone columns also similar procedure. But there are many more. Like if you have a consolidation, if you are building on a wetland, if you are going to build put a fill, and it's going to settle, means you can expedite the settlement with the there are techniques. You can do surcharge, and those are the improve the soils. How to improve at the same time? You can put shallow foundation. Some cases it wouldn't work, because if it is deep enough, you have to calculate. Then it might be better to go with the drill piers. It could be deep foundation system, and it could be drill piers. It's the same name. Here they use drill shafts. I think CIDH piles are commonly used in Sri Lanka, I believe, everywhere. Driven piles, you have steel piles, H piles. You can drive the piles, and if you have a good bearing strata, you can drive the piles. You can do the friction piles too. Helical piers, it's a small helical piers. If you have a small house and everything in the bad soil area, so it's like a stem, hollow stem. It has flights. You screw them, with the excavator mounted. Then you just go to the bearing, like a pretty good soils, then I generate, you can transfer the loads without going into the soft soils. And the micro piles also, you drill them and grout them with the bar, and you are trying to transfer the loads essentially, with the deep foundation system. As I said earlier, you can do the PT foundations for the expansive soils. These are the techniques for alternate foundation system. The shallow foundation, general foundation doesn't work. You can do the improvement. You can try to do the improvement or go with another foundation system. Okay, and I want to touch this. This is something special topic, So I already went through the shallow foundation and why, if it doesn't work, what we can do, improve the soils or do the deep foundations. So I want to touch base like some special topic, especially the dynamic foundation analysis, because I come across a lot because we do a lot of geothermal power plant projects. And geothermal power plants means, like you have the production wells, because you get your geothermal energy from the ground, because they will drill, like 1,000 feet, something like that, to get you a bigger heated source of water. Then use that water to produce electricity. Then they will inject back in the injection drill hole. So the energy comes, like from that, this heated steam or whatever, steam or water. So they get that energy to produce electricity. That's geothermal, pretty much. So there are a few companies they do, especially there's an Australian company. They do a lot of geothermal projects, and I do a lot of work for them. And so once you get your energy from the ground, steam, so you pass it through the turbine generator. So the turbine works and the generator produces electricity. So the turbine generator is, you may have 2 turbines with the generator in the middle, but these are huge equipment, they are rotating equipment. And so whenever I do the geotech investigation for those projects, so this is the main item because I need to consider, because you are going to have a turbine, because usually they are rotated at 1800 RPM. And they're very heavy. So they might be like 100 pounds means, 100,000 pounds, sorry. 100,000 means like, it's a lot of weight, just the generator, and the turbines also a lot, they weigh a lot. And the foundation size might be usually like a 20 feet, 6 meters by 40 feet, like 15. And it's very thick, it might be like a 3-4 meters thick, the foundation. And they place on, those are the shallow, they're still shallow foundations because they don't go deep, and they place those equipment and support. When they operate, they create dynamic loads, so they are operating. So what happens is, you can calculate all the bearing capacity and everything. You don't have settlement problem, and you can recommend the bearing capacity. The structural engineer will size the foundation right. And but still there could be some problem, because your dynamic loads, it creates a, it's a frequency. So it's going to operate in 1800 RPM, means it's a frequency, continuously operating that frequency. If that frequency matches you have a system of your turbine generator, machinery, and the foundation and the soil supporting. Everything together, it has a frequency. That's called a natural frequency. If your operating frequency matches your natural frequency, it doesn't matter about the foundation size. It's going to vibrate. It's going to vibrate and damage the equipment. That's So we, so like in the old days, before they started to analyze this, do this dynamic foundation analysis, old days, they just size it, just depending on your luck. Sometimes, it will work. Otherwise, they just make it very large. So sometimes 10 times the, so if you are talking about 100,000, like together 200,000 pounds means that's 100,000 kilograms. So if you want to size the foundation like 10 times, that's a lot of concrete, and it's a very large foundation you will end up with. So we do this dynamic foundation analysis to optimize the size. So yeah, what you want to avoid. So you want to avoid the resonance. That's called, yeah, if the equipment operating frequency and the natural frequency matches, that's called resonance. If it happens, then yeah, you are going to have problems. So what you do is, yeah, you find out your soil properties, and because the natural frequency depend on your soil system, because machinery, foundation, soil system, because everything together only the natural frequency. Foundation size, yeah, so it's going to vary depending on your, and you can size the foundation for those equipment to avoid those, because we try to do the size the foundation so it doesn't, it's person away from the operating frequency, because you need to calculate your natural frequency, and I just need to make sure it is 20% from the away from the operating frequency of the turbine generator. Okay, so yeah, like like you had to look at it's a imaginary frequency. Yeah, if you have an RPM, then you can calculate your imaginary frequency. That's very straightforward. Then the natural frequency of the system, I told you, like a equipment, your foundation, soil. So it will change. So you have vertical mode, your horizontal, rotation, torsional. So yeah, you're going to have various natural frequency, different vertical mode, one natural frequency. So everything shouldn't match, like all these cases shouldn't match. Whatever you calculate, it shouldn't match. So you should be 20% away. So that's a pretty tough, so you need to make sure everything works. And so how to calculate your natural frequency? So if you have the stiffness, you can calculate your natural frequency, because you have K over M, and M is the total mass, mass of the foundation plus a machinery system. That's the one sitting on the soils. And then your K is stiffness values. It's going to depend on your soil properties, spring stiffness value. So soil properties are, yeah, typically you need the shear modulus, Poisson ratio, you need weight and everything. So then since it's so complicated, so we try to do it in two methods. There are like two methods. It's called lumped sum method and elastic half space method. I have developed the spreadsheet and math sheet. Yeah, this one is in the spreadsheet and it's on in the math sheet, and there's a program also. Then you do the design in both methods, and you calculate for all those modes, and in two methods, and just make sure, because it's complicated analysis, because you want to make sure it works. So you do it in the two ways, and then you can make sure the foundation size is right, because you have a particular size. Yeah, you need a particular size. Yeah, say 15 by 40 feet. That's the size needed to place the equipment. Sometimes you may have to increase the size, you may have to increase the thickness, just to make sure to make the frequency work. So we try to, so how the application, this one vibration happens, it wouldn't be perfect, the equipment, if you have some kind of eccentricity, then only you will have a vibration issue. So yeah, these are the, I just want to show you the equations, and it depends on your soil properties and your weight of the turbine, weight of the generator, and these are the input parameters. Yeah, then you can calculate your natural frequency in various modes. This is one method, and this is elastic half space approach. So the shear velocity, if you see the shear velocity, yeah, that's when I said, yeah, geophysical testing, yeah, you can find out that value from the that testing and the borings and everything. If you have those information, you will have those input parameters. And these things, the equipment load, yeah, they will provide. Then we usually try to size the foundation 2 to 3 times the equipment weight. That's the kind of optimized. I don't want to go below 2 because yeah, like you want to optimize, it's a kind of a general rule of thumb, you just need to make sure at least you have 2. You try to optimize the size, because concrete cost a lot of money because especially this geothermal power plants, they build it somewhere nowhere. You don't have a concrete mix plant or anything. So because then you had to truck the concrete, it's far away, and they've had to do special things and everything. It costs a lot of money for the concrete. So when they build this geothermal power plant, so it's very important. Yeah, you just need to do this analysis. You don't want to put like a 10 times. If you put 10 times, that's like 5 times the. If I size it 2.26 times the weight of the equipment, that's a lot of savings. And but at the same time, you want to make sure it doesn't have vibration problem when it's operating. Typically, yeah. So this is the results. Yeah, I will. They will give me the foundation. The minimum foundation size. Then I will recommend. Okay, yeah, this is your the foundation width, foundation length has to be like that. This is for a project in Guatemala. Actually, I did some work for somebody, like some local firm did the geotech investigation, but they couldn't do the dynamic foundation analysis. So this company came back and wanted me to do that. And if you see these values, so you calculate your frequency ratio. Okay, so 1.58 means you are 58% away from the resonance. That's what it means. So in one method, yeah, I'm getting almost 20% away from the resonance, So I just want to make sure it's more than 1.2 or less than 0.8, this ratio, frequency ratio. Sometimes this, they will have 2 generators, So they will have an original generator, they will have a spare generator. They will say, yeah, they want to make it work for both generators. Okay, so yeah, then you have to do twice, and just to make sure, yeah, you do everything right for the both generator, because the weight changes. The rotational speed is same, but weight of the generator will change. Then yeah, everything will change, the frequency. Okay, I think that's it. I have.
Yeah, any questions, please?
I put this photo. It's probably a good example of bad geotech.
I have a question. Like, so if that star generator is also in the scene, are we going to have these 2 foundations as a monolithic one, or are we going to isolate these 2 foundations?
For the turbine generator?
Yes.
Yeah, it's just a monolithic. Yeah, it's a 1 pole. It's going to be a huge foundation. Yes.
So if one is not going to work, whether the other one will have this resonance will be in compliance.
So that's why, because yeah, if you go to the for example, I will show you the slide. So they have 2 generators, So you have a turbine and generator, and so I had to size this. I had to make sure this foundation width, length, and everything together works for turbine plus generator, the original generator, and all the spare generator. See, there's the same foundation. Foundation is not going to change, but whatever you calculate should work for everything. It's just a 1 foundation. It's a fairly small turbine generator, but yeah, I have designed a pretty large foundation too. It's a 1 foundation. Yeah, they will put the turbine in the generator in the middle. Turbine will be, because it's 1 shaft, no? Because turbine is the one getting the steam. So it rotates, and it rotates the generator. It creates electricity. So it's
is there a way that we can introduce the damper so that we can optimize the foundation design?
Dampers? Yeah. So, but the dampers, because yeah, you can dampen and change the stiffness value. But the thing is, those things cost too. You'd rather size the foundation right because and put it on the ground because it's less costly, you know, rather than damping because everything is bolted. You know, you have a structural frame and it is bolted in the foundation, and the equipment is supported on the foundation. So everything acts as a one system. Your equipment, turbine generator, and the foundation is buried. You know, foundation is, you know, like above ground 1 foot. It's like a 0.3 meter above ground, but everything else is buried, and everything as a system that creates a natural frequency. So it will have, that system will have a natural frequency. If you introduce a damping between the equipment and the foundation, so it's going to change things. So they want a solid, you know, so they don't want, you know, like a damp or anything, you know, it has to be attached to the foundation and should operate without vibration issue. So because it's continuously operate, you know, so the geothermal power plants, they never stop, you know, they continuously produce the power. So.
And the other thing is now you were mentioning about the collapsible soils and the expansible soils. So once these collapsible soils need to be removed, so like because since Sri Lanka is having a very less land space, so is there a way that we can dispose these collapsible soils and expansive soils? Because we do have such problems when we are getting, even when we are clearing some small sites, when we are getting this clay or some other stuff, say beach stuff or something, we are really facing hard to like
dispose. Yeah. So dispose means, you know, like the best place, you know, like a collapsible soils is not an issue because if it is not clay, you know, like collapsible soils are mostly like kind of silt. So it's not going to have an expansive property. So once you remove the collapsible soils and recompact, then you are not going to have issues. Clay soils are different. Okay, so once you remove, okay, so you want to remove like a, let's say 0.6 meters below the foundation, and it's a lot of soils you are going to remove. What you can do is, you could bury under the parking lot, or, you know, because they are a little bit very less sensitive to the expansive soils. That's how we put the recommendation, because if one site has a lot of expansive soils, then it's an issue because you cannot dispose, you know, like you can use the good soils as, but if it is all expansive soils, you may have to work with it. And we might recommend even, like, you know, putting the PT foundation and different alternates. You can place the expansive soils under the parking lot roadway, but that one also needs some separation. You know, you're going to have like instead of 1 meter of good soil, the parking lot and roadways and everything. So you might need only a 0.3 meter of good soils. It will perform fine. So. Because the building is a settlement sensitive, because whenever it's expand even a little bit, you are going to have cracks. But the parking lot, asphalt and everything, they are a little bit more flexible than, you know, the building. So they are not that much sensitive to settlement or expansion.
And what about these geotechnical investigations for the solar farms? Are we going to have any special forms of investigation or?
Solar power plants, you know, usually what they do is they drive piles, you know, because those are lightweight structures, and because you don't want to put like a lot of you know, concrete foundations, because they're lightweight structures, and they have these C-channel piles and small H piles, you know, small piles. They are like, you know, like they're kind of lightweight steel. Yeah, they drive those piles, and, you know, they don't have to go that much deep. And so we do the borings, you know, typically, because we need the block counts and everything. But you don't have to do tons of borings, because even if it's like, you know, I did a solar power plant, you know, it was like and it was like a 15 acres. So yeah, I did like a 10 boring. So you want to make sure, yeah, the soils are okay, you know. And we'll include the recommendation. And sometime, you know, like in most cases, the owner will do a pile testing. Then we will go and inspect those things and review those things, because that's going to be tons of piles, you know, like a small piles, but you need a lot of piles. So they usually like to do the pile testing, driven pile testing, to test the loads and everything, the condition, and then they use that information also.
And when these settlements are being measured with the filling, so like is it good to have the fills in like layer by layers and to keep it in a time frame to get the consolidated or
Yeah,
any other forms of settlement?
yeah, it has to be placed in layers, you know.
Layers,
So
yeah.
even if it is placed in layers, yeah, so usually, because yeah, the foundation recommendations are only one part of the, you know, the geotech report. We will have the recommendation how to place the soils, how to cut it, you know, how you are going to cut it, and what are the difficulties. Can you cut it? And, you know, like, can you remove, can you use the typical excavation equipment to remove it, and how you want to place it. Yeah, what is the maximum thickness? Okay, so you can place the fill only in 0.3 meters maximum thickness, and each layer has to be compacted to a certain density. Okay, so the relative compaction, usually, like, you know, like for commercial projects with the thick fills, yeah, it will be 95% compaction. So even when you place like a compacted fill, you know, the fill, it is not 100% compaction. Okay, so fill can still settle, you know. So because yeah, if you have a 1 foot layer of fill, on top of it, if you're going to put a 20 feet of layer of fill, that's a lot of weight. And so that can settle. So it takes a little bit of time for that settlement to happen. So that's what I say, yeah, fill settlement is what is happening inside the fill layer. It's not significant, because if it is a 0.5%, let's say if it is a 10 feet, that's only 1 inch, you know. So it will happen, half of it will happen when you place the fills and compact it. So 0.5 inches will remain, but so it's not a big deal. But whenever you have, you know, some sites, you know, I dealt with it, yeah, like there's 50 feet of fill, so then it's an issue. So yeah, if you have 50 feet of, yeah, for example, Tesla Gigafactory, yeah, they had like 60 feet of fill. So we had to, you know, it will take time for that one to, you know, even if you placed in a compacted layer by layer, so you're going to have some fill settlement, but it will happen pretty quickly, you know, within 3 months. But yeah, we put some settlement monitoring and make sure that it does happen quickly. So just to verify.
And this one final question. So if that we are going to have this foundation on the collapsible soil, say if it is going to be a building which going over a long span, the PT is not going to be like economical. So in that case, are we going to remove the collapsible soils and we are going to make stabilize the residual soil, or what would be the most economic way to go in that case?
Yeah, you can remove it, and, you know, so because the collapsible soils to collapse, you need water, moisture. Okay, so you can control the, you know, you remove it, like, you know, let's say 1 meter or something like that. Yeah, depending on, you know, your footing sizes and everything, you may have to go even a little bit deeper and remove it and replace in compacted layer. Then you are not going to have collapsible potential. So. Because the soils below, yeah, even if there's a deep soil, you can try to control the moisture. So you give the slope and everything, and, you know, or you can put some. Is that for a building or is that for a roadway?
Probably it's if you are going for a building.
Yeah, so building means, yeah, you can control the moisture. Yeah, then you can, yeah, you could even include some moisture like a cutoff and stuff around the building, then you're just protecting the collapsed soils below the removal layer.
Okay. So any other questions?
Anybody else?
Yeah, Anand, I have one question. Yeah, is there any equation for the what the depth for the shallow foundation? That I saw that width is there. That one equation you have mentioned in that previous slides.
Yeah, let's see. We'll go to the slides. This one?
No, that yeah, the depth is there. No, I am not asking for the wearing capacity. That the depth of the shallow normally.
Okay, so let's see. Yeah, soil report. Yes, I think probably it's under the geotech report. Yeah, minimum foundation depth of frost. Is that right?
Yeah. Is there any equation or?
Yeah. So usually, so you don't have, we don't have a frost problem. Here, especially in my area, it gets a lot of snow, and winter it gets. Yeah, so I didn't even go into that one, because usually, like, so your depth of foundation is going to be based on your sliding, and if you have a passive resistance, if you want to give a passive protection, like a typically, like 2 feet is a good depth, 0.6 meters, because you don't want to undermine the foundation and everything. If you don't have frost tissue, that's the main thing you want to consider. Typically, like even without frost tissue, so we recommend like like a 2 feet foundation depth, because if you undermine the foundation, if the soils are removed and everything, it's a problem. So it's better to have the exterior foundation for the building sufficiently deep. In Sri Lanka, you don't have, you'll have the wind load. So then you have a lateral issue too. So then if you bury the foundation deep enough, you can depend on your passive soil pressure to resist some of the lateral load too, if you place it deep enough. Otherwise, like a typically 2 feet is a good value, 0.6 meters. But here the frost depth is, it is defined by all the agencies here. Here in my areas, because depending on how deep the freezing can occur, because whenever in the winter time, the soil can freeze. Soil can freeze to, let's say, if it is freezing to 18 inches, what's going to happen is if the soil freezes, and whenever it's thrown back, then you're going to lose some density. So that's a problem. So you want to place the foundation below that frost depth. So all the agencies will define, and there are charts, in the International Building Code and everything. So you can find out what is your frost depth. If you go to, like for example, Alaska is a very northern region, or in Canada, probably in Toronto and everything. So they might have a deeper frost depth. So they will have to go below that. Does it explain that one?
Yes, yeah. Okay, thanks, Anand. Okay. Yeah, that I am asking another thing, that in clay, that normally I have to construct that 5-story building. So that wearing capacity of the soil maybe 75 kilonewton per meter square. So normally what is the foundation we have recommended?
75 kilonewton per meter square. Let's see. What is that in PS?
Is it go for the raft or that?
Yeah, that seems a pretty high load, no? Yeah, let's see what is that load. I'm just trying to convert it. 75, no? Right.
Yeah, 5-story means normally that each floor 15 kilonewton per meter square, right?
Yeah, so you can do draft means mat foundation. So that might be easier to support.
That there is no issue, that surrounding area maybe that high stress is there, that close to that boundaries.
You could, yeah, you could have, but like,
Yeah.
yeah. So if it is close enough, but what is it depends on your the building size too, because your influence there. Usually, like if you have a, let's say, if you have a 10 meter, then like your stress distribute like a typically 1/2 from the soil, from the foundation edge. So if you are the next building is sufficiently far enough, so it may not influence. Or you can go deeper, then you are not influencing into their foundation or anything. So like if you take a foundation like here, so this load, how the bearing load distribute is, this slope is 2 to 1, sorry, 1/2 to 1. This is 1/2, this is 1. So that's how your load distribution is. How it is, distributed in the soils.
Any other questions?
Or you can use the pile foundation. It's common, like in 5-story buildings, probably not. It's not worth to do the piles and stuff. Cellar foundation, mat.
Yeah, shall I get any presentation, or are you give that these presentation slides?
The presentation slides have been already.
Yeah,
presented.
I can.
I think
yeah,
that will be circulated by our assistant secretary soon.
Okay, Ramanan. Okay.
Any other questions? Shall we
Any
wind
other
up the
question?
session?
All good.
Seems all good.
என்ன எல்லாம் தமிழாக்கள் தானே? வேற இல்ல நான் தமிழ் எடுத்துட்டேன்.
இல்ல அதுல நின்றவங்க இப்ப போயிட்டாங்கன்னு நினைக்கிறேன்.
Okay.
Okay, if there are no questions, so we can bind up the session. So it's the time to convey the thanks to engineer P. Vimalaraj. Actually, this is his second session with the IESL Eastern Center during the last 2 years, it seems. And that was a very...
Hello?
Sorry, I'm getting the phone. So that was an educative and informative session. So thank you, Anand. And we hope to have more sessions with you in future as well.
Okay, sure.
Thank you. Thanks a lot.
Yeah, not a problem. I'll stop the sharing.
Thank you.
Sure, thanks.
Thank you very much, Anand. Thank you.
Yeah, welcome.